Imagine you are floating in the void of space. There is no sound, there is no wind, there is nothing around you except the endless black canvas of the universe, dotted with the faint glow of distant stars. Everything looks peaceful. Everything looks still. You feel weightless, calm, suspended in the most serene environment you have ever experienced. But here is what you do not know. Right now, at this very moment, thousands of invisible particles are tearing through your body. They are moving at nearly the speed of light. They are smaller than atoms, yet each one carries the energy of a speeding bullet. They are ripping through your skin, passing through your muscles, penetrating your bones, and striking your DNA with enough force to shatter the molecular bonds that hold your genetic code together. You cannot see them. You cannot feel them. You cannot hear them. There is no alarm going off. There is no pain. There is no warning of any kind. And yet, with every second that passes, your body is being slowly destroyed from the inside out. Your brain cells are being hit. Your heart tissue is being damaged. The delicate strands of your DNA are being broken apart, piece by piece, in ways that your body may never be able to repair. This is not science fiction. This is not a horror movie. This is the measured, documented, scientifically proven reality of what happens to every single human being who leaves the protective bubble of planet Earth. And this is the story of why cosmic radiation is not just a challenge, not just a risk, not just a problem to be solved, but potentially the single greatest invisible wall that nature has placed between humanity and the stars. Before we go any further, I want you to think about something. We talk about space travel as if it is inevitable. We see movies about colonizing Mars, about traveling to other star systems, about spreading human civilization across the galaxy. We build rockets. We plan missions. We design habitats. We talk about timelines, about when we will get to Mars, when we will reach the outer planets, when we will send humans to other stars. But almost nobody talks about the one problem that has no proven solution. Almost nobody mentions the invisible force that could make all of those dreams physically impossible for biological beings like us. That force is cosmic radiation. And today, we are going to understand it completely. We are going to understand where it comes from, what it actually is at the most fundamental level, how it interacts with human biology, why conventional shielding does not work the way you think it does, what happens to the human brain when it is exposed to these particles for months or years, and why this problem gets exponentially worse the further you travel from Earth. We are going to look at real measurements, real data, real experiments, and real incidents that prove just how dangerous this invisible force truly is. And by the end of this journey, you will understand why some scientists believe that cosmic radiation may be the ultimate boundary, the final limit that determines how far biological life can travel in this universe. Now, I want to start with a story, a real story. A story that involves one of the luckiest coincidences in the entire history of human spaceflight. And it begins in the year 1972. In April of 1972, the Apollo 16 mission returned safely to Earth. Astronauts John Young, Thomas Mattingly, and Charles Duke had spent 11 days in space, including nearly 3 days on the surface of the Moon. They came home healthy. They came home triumphant. Another successful mission in the Apollo program. NASA was already preparing for the final Apollo mission, Apollo 17, which was scheduled to launch in December of that same year. Everything was going according to plan. The moon missions had become almost routine in the public eye. People had started to lose interest. The danger seemed manageable. The universe seemed cooperative. But then, something happened between those two missions. something that NASA did not predict, could not prevent, and barely even understood at the time. Something that, had it occurred just a few months earlier or a few months later, could have killed astronauts in space and potentially ended the entire Apollo program in tragedy. On August 2nd, 1972, a region on the surface of the Sun, designated McMath 11-976, began to erupt. This was a sunspot region, a magnetically complex area of the solar surface where intense magnetic field lines twisted and tangled together, building up enormous amounts of energy. Over the next 9 days, from August 2nd to August 11th, this single region produced 67 individual solar flares. Not one, not five, 67. Among these were 4 flares classified as X-class, the most powerful category of solar flare that exists, and one of them, the so-called seahorse flare that erupted on August 4th, was later estimated to be an X-20 class event. To put that in perspective, an X-20 flare is among the most powerful solar explosions ever recorded in human history. It released energy equivalent to billions of nuclear bombs detonating simultaneously. But the flare itself was not the truly dangerous part. What followed the flare was far worse. A massive coronal mass ejection, a CME, was launched from the Sun directly toward Earth. A coronal mass ejection is a billion-ton cloud of magnetized plasma, superheated material from the Sun's corona, blasted outward at incredible speed. Normally, a CME takes 2 to 3 days to travel from the Sun to the Earth, a distance of about 150 million kilometers. This one made the journey in just 14.6 hours. That is the fastest Sun-to-Earth transit time ever recorded for a coronal mass ejection. The solar wind speed exceeded 2,000 kilometers per second. That is 0.7% of the speed of light. Material from the Sun was traveling at nearly 1% of light speed toward our planet. When this smear hit Earth's magnetosphere, it compressed our protective magnetic shield to less than 20,000 kilometers from the surface. Normally, the magnetosphere extends 60,000 to 75,000 kilometers on the Sun-facing side. The storm was so powerful that it squeezed our magnetic protection to a fraction of its normal extent. On the ground, the effects were dramatic. Aurora was visible as far south as Spain. In the southern United Kingdom, the aurora was bright enough to cast shadows. AT&T reported a 60-volt surge on long-distance telephone cables in the United States. Satellite electronics were damaged, with some satellites aging by 2 years in a matter of hours. And in the waters near the Vietnamese port of Haiphong, dozens of American magnetic-influenced sea mines spontaneously detonated. These mines were designed to detect the magnetic signature of passing ships. The geomagnetic storm was so intense that it triggered their firing mechanisms from thousands of kilometers away. But here is what matters most for our story. During this event, the flux of solar energetic particles in space reached staggering levels. Proton flux at energies above 10 million electron volts reached approximately 70,000 particles per second per steradian per square centimeter. This was classified at the S4 to S5 level on the space weather scale, the highest and most dangerous category. If a human being had been in deep space during this event, outside the protection of Earth's magnetosphere, the radiation dose they would have received has been estimated at between 1,000 and 4,000 millisieverts over just a few hours. To understand what that means, you need to know that a dose of 1,000 millisieverts causes acute radiation sickness, including nausea, vomiting, fatigue, and significant damage to the immune system. A dose of 4,000 millisieverts has a 50% fatality rate within 30 days, without medical treatment. And this dose would have been delivered in hours, not over a career, not over a lifetime, but in the span of a single afternoon. Now here is the critical detail. The Apollo spacecraft provided some shielding, enough to block perhaps 90% of incoming solar protons at certain energies. But even with that reduction, an astronaut inside the Apollo command module could still have received several hundred millisieverts, enough for acute radiation sickness. And an astronaut performing an extravehicular activity, a moonwalk, wearing only a spacesuit? They could have received a lethal dose. They could have died on the surface of the moon, killed by invisible particles from the sun, with no warning and no way to escape. Apollo 16 returned to Earth on April 27th. This solar storm occurred in early August. Apollo 17 launched on December 7th. The storm fell exactly in the gap between missions. If Apollo 16 had been delayed by 3 months, or if Apollo 17 had been moved up by 4 months, astronauts would have been in deep space during the most powerful solar radiation event of the decade. NASA got lucky. Extraordinarily lucky. And this event became one of the most studied case studies in space radiation history, because it proved something that many engineers had been reluctant to accept. Space radiation is not just a long-term health concern. It is not just something that increases your cancer risk over decades. It can be an acute, immediate, and rapidly lethal force. It can kill you in hours. And it can do so without any visible warning, without any sensation, without any way for you to know it is happening until the symptoms of radiation poisoning begin. This story from 1972 is our entry point into a much larger and much more troubling reality. Because that solar storm, as terrifying as it was, represents only one type of space radiation, and arguably not even the most dangerous type. The solar particles from that event were mostly protons with energies below 1 billion electron volts per nucleon. They are relatively easy to shield against if you have enough material and enough warning time. The far more insidious, far more penetrating, and far more difficult problem is galactic cosmic radiation. And that is what makes cosmic radiation not just a temporary hazard during solar storms, but a permanent, continuous, unrelenting invisible wall that exists everywhere in deep space, every second of every day, with no off switch and no shelter that we currently know how to build. Now let us understand what cosmic radiation actually is. Not in vague terms, not in simplified analogies. Let us understand it at the most fundamental level, as physics describes it. Cosmic radiation is a broad term that encompasses all high-energy particles traveling through space. But it has 2 primary components that matter for human space exploration. The first is solar particle events, which we have already discussed. These are bursts of energetic particles, mostly protons, released during solar flares and coronal mass ejections. They come from our own sun. They have energies typically below 1 billion electron volts per nucleon. They are sporadic, unpredictable, and can be intense but short-lived. And they can, in principle, be shielded against with sufficient material. The second component is galactic cosmic rays, often abbreviated as GCR. And this is where the real problem lies. Galactic cosmic rays do not come from our sun. They come from outside our solar system entirely. They originate from the most violent events in the universe: supernova explosions, the death throes of massive stars, where the collapsing stellar core sends shockwaves through surrounding material at speeds approaching that of light. Active galactic nuclei, the supermassive black holes at the centers of galaxies that accelerate matter to incredible energies before ejecting it in powerful jets. Neutron-star collisions, gamma-ray bursts, and other energetic astrophysical phenomena that we are still working to fully understand. These events act as natural particle accelerators, far more powerful than anything humans have ever built. They take ordinary atomic nuclei, the nuclei of hydrogen, helium, carbon, oxygen, silicon, iron, and they accelerate them to speeds so close to the speed of light that their kinetic energies become almost incomprehensible. Let me tell you about the composition of galactic cosmic rays. Approximately 87% of GCR particles are protons, the nuclei of hydrogen atoms. About 12% are alpha particles, which are helium nuclei consisting of 2 protons and 2 neutrons. And approximately 1% are heavier nuclei, atoms stripped of all their electrons, traveling at relativistic speeds. This 1% might sound insignificant, but this 1% contains some of the most destructive particles in the known universe. They are called Z particles. HZE stands for high atomic number and high energy. These are the nuclei of heavy elements like carbon, oxygen, silicon, and iron, moving at nearly the speed of light. An iron nucleus with an atomic number of 26, traveling at 90% of the speed of light, carries an absolutely devastating amount of ionizing potential. When it passes through matter, including biological tissue, it strips electrons from every atom in its path. It creates a trail of destruction at the molecular level that is completely unlike anything produced by lower energy radiation. A single iron Z particle can damage or destroy thousands of molecules along its track through your body. It tears through DNA like a bullet through tissue paper, creating not just one break, but clusters of breaks, chemical modifications, and crosslinks that overwhelm your cellular repair mechanisms. Now, let me give you a sense of the energies involved. The energy spectrum of galactic cosmic rays is extraordinarily broad. It ranges from about 10 million electron volts at the low end to beyond 10 to the power of 20 electron volts at the extreme high end. Most GCR particles have energies in the range of hundreds of millions to a few billion electron volts per nucleon. But the spectrum extends to energies that are almost impossible to comprehend. On October 15, 1991, a detector called the Fly's Eye, located in the desert of Utah in the United States, detected a single cosmic ray particle with an energy of 3.2 times 10 to the power of 20 electron volts. That is 320 exa-electron volts. The scientists who detected it were so shocked that they named it the "Oh my God" particle. To understand what this energy means in human terms, consider this. That single subatomic particle, smaller than an atom, carried the same kinetic energy as a baseball thrown at about 100 kilometers per hour. The energy of a professional pitch, concentrated entirely in a single proton. That particle was traveling at 99.999999999999999999999999999% of the speed of light. It was so close to the speed of light that if it raced a photon across the observable universe, it would arrive only a fraction of a second behind. One particle, smaller than an atom, carrying the energy of a macroscopic object in motion. This tells you something profound about the universe we live in. Nature has created particle accelerators that make our most advanced technology look like toys. The Large Hadron Collider, the most powerful particle accelerator ever built by humans, reaches energies of about 13 tera-electron volts. The Oh my God particle had an energy roughly 20 million times greater than what the LHC can produce. 20 million times. And particles like this are traveling through space right now. Not often at those extreme energies, but the continuous background of galactic cosmic rays at lower but still devastating energies is constant, relentless, and everywhere. In November 2023, a collaboration using the telescope array in Utah detected another ultra-high energy particle with an energy of 2.4 times 10 to the power of 20 electron volts. They named it the Amaterasu particle, after the Japanese sun goddess. This was the second highest energy cosmic ray ever detected. Its origin is mysterious, because when scientists traced its trajectory back, it appeared to come from a region of space with no known energetic source. A void. An empty region, as if the particle appeared from nowhere. This remains unexplained and adds to the deep mystery of cosmic ray origins. But you do not need particles at those extreme energies to create a serious problem for human biology. The vast majority of damage comes from the much more common GCR particles at energies of hundreds of millions to billions of electron volts per nucleon. These are too energetic to be fully stopped by any practical amount of shielding material, yet they deposit enough energy in tissue to cause serious biological damage. And they are everywhere, in every direction, at every moment, throughout the entire volume of interplanetary and interstellar space. They are the background noise of the cosmos, the constant bombardment that everything in space experiences, and they are what makes cosmic radiation fundamentally different from all other space hazards. To truly understand why cosmic radiation is such an impenetrable wall, you need to understand the layers of protection that Earth provides. Because here on the surface of our planet, we live our entire lives bathed in cosmic radiation and barely notice it. We receive approximately 0.3 millisieverts per year from cosmic rays at sea level. A tiny, manageable amount. But this is not because cosmic rays are weak. It is because we are protected by the most extraordinary series of natural shields ever assembled. 4 concentric layers of defense that work together to reduce the cosmic radiation reaching our bodies by a factor of hundreds or even thousands. And every single one of these layers disappears the moment you leave Earth. The first and outermost layer is the heliosphere. The heliosphere is a vast bubble in interstellar space created by the solar wind, the continuous stream of charged particles flowing outward from the sun in all directions. This wind of particles carries the sun's magnetic field outward, inflating a protective bubble that extends approximately 120 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, about 150 million kilometers. So the heliosphere extends roughly 18 billion kilometers in every direction. This bubble acts as a shield against galactic cosmic rays. The solar magnetic field carried by the wind interacts with incoming GCR particles, deflecting many of them, slowing others, and reducing the overall intensity that penetrates to the inner solar system. During solar maximum, when the sun is most active and the solar wind is strongest, this shielding effect is enhanced. During solar minimum, when solar activity is low, the heliosphere provides less protection and more GCR penetrates inward. This creates an interesting paradox that we will explore later. How effective is this heliospheric shielding? We have direct measurements. NASA's Voyager 1 spacecraft crossed the heliopause, the boundary of the heliosphere, on August 25, 2012. It became the first human-made object to enter interstellar space. Voyager 2 followed, crossing the heliopause on November 5, 2018. Both spacecraft carry cosmic ray detectors, and the data they returned was striking. As each Voyager crossed from the heliosphere into interstellar space, the galactic cosmic ray intensity jumped dramatically. The measurements confirmed that the heliosphere blocks more than 70% of the galactic cosmic radiation that would otherwise flood the inner solar system. 70%. Just from this one layer. Without the heliosphere, the cosmic radiation intensity throughout our entire solar system would be more than 3 times what it currently is. Every planet, every moon, every asteroid within the heliosphere benefits from this protection. And any spacecraft traveling beyond the heliopause loses it entirely. The second layer of protection is Earth's magnetosphere. Our planet has a powerful magnetic field generated by the churning of molten iron in its outer core. This magnetic field extends far into space, creating a region called the magnetosphere that deflects most charged particles away from Earth. The magnetosphere extends approximately 60,000 to 75,000 kilometers toward the Sun, and stretches into a long tail of more than 300,000 kilometers on the night side. Charged particles from space, including those galactic cosmic rays that penetrate the heliosphere, encounter Earth's magnetic field and are deflected, channeled, or trapped. Many particles get caught in the Van Allen radiation belts, two donut-shaped regions of intense radiation that encircle Earth at distances of approximately 1,000 to 6,000 kilometers for the inner belt, and 13,000 to 60,000 kilometers for the outer belt. These belts are actually concentrations of trapped energetic particles, dangerous in their own right, but serving as evidence that Earth's magnetic field is actively capturing and containing particles that would otherwise reach the surface. The magnetosphere is strongest at the equator and weakest at the poles, which is why aurora, the visible glow of atmospheric gas excited by incoming particles, occurs primarily near the polar regions. At the poles, some particles do make it through, following magnetic field lines down into the upper atmosphere. The third layer is Earth's atmosphere itself. Even those cosmic ray particles that successfully penetrate both the heliosphere and the magnetosphere must still contend with Earth's atmosphere. And the atmosphere is an extraordinarily effective radiation shield. The total mass of air above you at sea level provides shielding equivalent to approximately 1,000 grams per square centimeter of material. To visualize what this means, imagine that above your head right now, there is a wall of material with the same radiation stopping power as 10 meters of water, or 3 meters of concrete. This is what our atmosphere provides. When high-energy cosmic rays enter the atmosphere, they collide with nitrogen and oxygen nuclei at high altitude. These collisions create showers of secondary particles, cascades of fragments that spread out as they descend. But critically, most of the energy is absorbed or dispersed during this process. By the time anything reaches sea level, the dangerous primary cosmic ray has been broken down, and its energy distributed so widely that the remaining radiation at ground level is minimal. Only the very highest energy cosmic rays produce secondary particles that reach the surface with any significant energy. This is why commercial aviation exposes you to more cosmic radiation than standing on the ground. At airplane cruising altitude of 10 to 12 kilometers, you are above a significant fraction of the atmosphere's shielding. Flight crews on long-haul polar routes can receive several times the radiation dose of the general population. But even at airplane altitude, you still have most of the atmosphere below and around you. The difference between sea level and airplane altitude is perhaps a factor of 10 to 100 in cosmic ray dose. Now, imagine removing the atmosphere entirely. The difference between sea level and space is a factor of hundreds. The fourth layer is less about cosmic rays specifically, but is worth mentioning as part of Earth's overall radiation protection system. The ozone layer, concentrated at approximately 20 to 30 kilometers altitude, primarily absorbs ultraviolet radiation from the sun rather than cosmic rays. But it represents yet another component of the multi-layered system that makes Earth's surface so remarkably well protected compared to anywhere else in the solar system. Now here is the crucial insight. When you are on the International Space Station, orbiting at approximately 400 kilometers altitude, you are above the atmosphere but still within Earth's magnetosphere. You have lost the atmospheric shield, but you retain the magnetic protection. Astronauts on the ISS receive approximately half to 1 millisievert per day. This is roughly 100 to 300 times the rate at Earth's surface, but still manageable for missions of several months to a year. The magnetosphere is still doing significant work to reduce the radiation environment. But the moment you leave Earth's magnetosphere and travel into deep interplanetary space, you lose that magnetic protection. You are now exposed to the full intensity of galactic cosmic rays that have penetrated the heliosphere. Measurements from NASA's Mars Science Laboratory mission, using the Radiation Assessment Detector instrument aboard the Curiosity rover during its transit from Earth to Mars in 2011 and 2012, showed a dose-equivalent rate of 1.84 millisieverts per day in deep space. This is roughly 2 to 4 times higher than what ISS astronauts experience. And this is the continuous background rate, the constant dose that accumulates every single day, with no respite, no shelter, no way to turn it off. Each layer you remove from Earth's protection system creates an exponential increase in radiation exposure. Earth's surface, 0.3 millisieverts per year from cosmic rays. Aeroplane altitude, perhaps 3 to 5 millisieverts per year from cosmic rays. Low Earth orbit, 180 to 360 millisieverts per year. Deep interplanetary space, approximately 670 millisieverts per year. Interstellar space beyond the heliopause, potentially more than 2,000 millisieverts per year. This is the gradient. This is the invisible wall. Not a sharp boundary, but a progressively intensifying field of radiation that becomes more and more lethal the further you travel from Earth's protective embrace. If you are watching this and finding your perspective on space travel fundamentally shifting, if you are realizing that the universe is far more hostile than you imagined, then I want you to share this understanding with others. Hit the subscribe button. Leave a comment telling me what surprises you most about this topic. Because we are only getting started. We have not even discussed what this radiation does to the human body at the cellular level, why building thicker shields actually makes things worse, or why scientists believe we may be fundamentally trapped within a radiation boundary that we cannot cross with our current biology. Let us now dive into what happens at the biological level when cosmic radiation enters your body. This is where the story becomes truly disturbing, because the mechanisms of damage are elegant in their destructive efficiency. First, you need to understand what ionizing radiation does at the most basic chemical level. All matter is made of atoms. Atoms consist of a nucleus containing protons and neutrons, surrounded by clouds of electrons. Chemical bonds between atoms, the bonds that hold molecules together and give structure to proteins, and every other biological molecule, are formed by the interactions of these electrons. When a high-energy cosmic ray particle passes through matter, it interacts electromagnetically with the electrons of atoms in its path. Its enormous kinetic energy and electrical charge rip electrons away from atoms, a process called ionization. Each ionization event creates a positively charged ion and a free electron. These ions and free electrons are chemically reactive. They can break molecular bonds, alter the shapes of proteins, and damage the structure of DNA. There are two primary mechanisms by which this damage affects your cells. The first is direct damage. This occurs when a cosmic ray particle or its secondary radiation directly strikes a critical biological molecule, particularly DNA. The energy deposited breaks the chemical bonds of the DNA backbone, potentially breaking one strand or both strands of the double helix. The second mechanism is indirect damage. Since biological cells are approximately 70% water, most cosmic ray ionization events occur in water molecules. When water is ionized, it produces highly reactive chemical species called free radicals, particularly hydroxyl radicals. These are extremely reactive molecules with unpaired electrons that will attack and damage any biological molecule they encounter, including DNA. Indirect damage from free radicals is estimated to account for approximately 60 to 70% of all radiation-induced DNA damage in cells. Now here is where the nature of cosmic radiation makes it uniquely dangerous compared to other forms of radiation. Different types of radiation deposit their energy in different patterns. Medical X-rays, for example, deposit energy relatively sparsely along their path. They cause scattered, individual ionization events that are spread out. Your cells have evolved sophisticated DNA repair mechanisms that can handle this type of damage quite effectively. Single-strand breaks are repaired within minutes. Even isolated double-strand breaks can usually be repaired within hours, albeit with a small probability of error. But Z particles, the heavy nuclei in galactic cosmic rays, deposit their energy in a completely different pattern. Because of their high charge and high energy, they create an extremely dense track of ionization. As an ion nucleus passes through your tissue at relativistic speed, it creates thousands of ionization events within a tiny cylinder around its path. The diameter of this damaged track can be nanometers to micrometers, but within that track, the destruction is absolute and total. Every molecule in the particle's path is ionized, fragmented, and destroyed. This creates what radiation biologists call clustered damage or complex damage. Within a tiny region of DNA, you get not just one break, but multiple breaks, base damages, crosslinks between DNA strands, crosslinks between DNA and attached proteins, and chemical modifications all concentrated together. This type of damage is qualitatively different from sparse ionization. Your cellular repair mechanisms are simply not designed to handle it. They evolved to cope with the low-density damage from natural background radiation on Earth. When they encounter a densely damaged cluster, they either fail to repair it properly or give up entirely. Either outcome is bad. Improper repair leads to potentially cancerous mutations. Cell death, when it occurs in tissues with low regenerative capacity like the brain, means permanent loss of function. This concept of linear energy transfer, or LET, is crucial to understanding why cosmic radiation is so much more dangerous than other radiation types at the same total dose. LET measures how much energy a particle deposits per unit length of its path through material, typically measured in kilo-electron volts per micrometer. X-rays have a low LET, around 2 kilo-electron volts per micrometer. Protons have a moderate LET, but ions at cosmic ray energies have an extremely high LET, depositing hundreds of kilo-electron volts per micrometer. The biological damage per unit of energy deposited is far greater for high-LET radiation than for low-LET radiation. This is quantified by a factor called the relative biological effectiveness, or the radiation quality factor. For Z particles, this factor can be 20 to 40 times higher than for X-rays, meaning that 1 gray of Z radiation causes 20 to 40 times more biological damage than 1 gray of X-ray radiation. This is why you cannot simply compare cosmic radiation doses to medical radiation doses and assume equivalent effects. The quality of the radiation matters enormously, and cosmic radiation is the highest quality radiation environment that humans can encounter. Let us now talk specifically about cancer, because this is the most well-quantified risk of cosmic radiation exposure. NASA officially designates space radiation as the #1 risk to astronaut health for missions beyond low Earth orbit. The reason is straightforward. Ionizing radiation causes mutations in DNA. Some of these mutations occur in genes that control cell growth and division. When these control genes are mutated, cells can begin to grow uncontrollably. This is cancer. The relationship between radiation dose and cancer risk has been studied extensively using data from atomic bomb survivors in Hiroshima and Nagasaki, nuclear industry workers, medical radiation patients, and animal experiments. For low-level radiation like X-rays, the risk increases approximately linearly with dose, with no safe threshold. For high-level radiation like Z particles, the risk per unit dose is significantly higher. What does this mean for a Mars mission? Based on measurements from the Curiosity rover's RAD instrument, a reference Mars mission of approximately 1,000 days would expose astronauts to a total dose equivalent of approximately 1 sievert, or 1,000 millisieverts. Research published by scientists at Colorado State University found that this level of exposure gives astronauts greater than a 3% risk of dying specifically from radiation-induced cancer. This might sound small, but remember that this is in addition to their normal baseline cancer risk. And 3% risk of death from a single mission is far higher than what most space agencies consider acceptable. ESA's radiation limit for an astronaut's entire career is 1,000 millisieverts, meaning a single Mars mission could potentially use up the entire career radiation budget in one go. NASA's limit, revised in 2022 to 600 millisieverts regardless of age or sex, is even more restrictive. Under NASA's current guidelines, a Mars mission as currently planned may not be approvable because it could exceed the career dose limit. The cancer risk is not limited to any single organ. Studies have identified increased risks for lung cancer, colon cancer, leukemia, breast cancer in women, liver cancer, bladder cancer, thyroid cancer, and others. Research on Apollo astronauts and IS crew has shown elevated rates of various cancers compared to matched populations, though the sample sizes are small enough that definitive conclusions are difficult. What is clear is that the risk is real, quantifiable, and increases with dose in a way that makes long-duration deep space missions genuinely dangerous. But cancer is not the only biological consequence, and some scientists argue it is not even the most concerning one for mission success. Let us talk about the brain. The central nervous system, your brain and spinal cord, is what makes you who you are. It controls your thoughts, your memories, your decision-making, your motor skills, your emotions, and every other aspect of your conscious experience. And it is extraordinarily sensitive to cosmic radiation. In 2023, a team of researchers led by Kokon published a comprehensive review in the journal Biology examining what galactic cosmic rays do to the central nervous system. Their analysis drew on decades of animal studies exposing mice, rats, and primates to radiation types and doses, simulating what astronauts would experience on deep space missions. The findings are sobering. Radiation at space-relevant doses causes measurable structural and functional changes in the brain. In rodent studies, exposure to Z particles at doses equivalent to a Mars mission causes a reduction in the complexity of neuronal dendrites, the branching structures that neurons use to communicate with each other. Dendritic spines, the tiny protrusions where most neural connections occur, are reduced in number. This is not a subtle finding. The physical structure of brain cells is being simplified, pruned, degraded by radiation exposure. And unlike many other cell types in the body, neurons have extremely limited regenerative capacity. When a neuron is damaged or killed, it is generally not replaced. The loss is permanent. A study from Stanford Medicine, published in 2019, specifically examined chronic irradiation, the type of continuous low-dose exposure that astronauts would experience in deep space. They exposed mice to chronic low-dose radiation, simulating the space radiation environment, and found significant physiological and behavioral deficits. The mice showed impaired recognition memory, reduced spatial memory performance, increased anxiety-like behavior, and altered social interaction patterns. These are not minor effects. For astronauts on a multi-year mission to Mars, making complex decisions, operating sophisticated equipment, handling emergencies, and maintaining psychological stability in isolation, any cognitive impairment could be mission critical. A crew that is progressively losing memory function, experiencing increased anxiety, and suffering impaired decision-making over the course of a 2 to 3 year mission faces a compounding risk that grows worse with every passing month. Frank Cucinotta, one of the most prominent researchers in space radiation biology and formerly NASA's chief radiation health officer, published a detailed analysis in 2014 describing the potential central nervous system risks during deep space missions. His assessment included detriments in short-term memory, reduced motor function, and behavioral changes as possible consequences of GCR exposure during a mission. These are not long-term post-mission effects. These could manifest during the mission itself, potentially compromising crew performance at the exact moments when sharp cognition is most critical, such as during orbital insertion maneuvers, landing procedures, or emergency responses. Let me share some specific numbers that illustrate the scale of the problem. Calculations by Curtis and colleagues estimated that during a 3-year Mars mission at solar minimum, approximately 2 to 13% of critical sites in central nervous system cells would be directly struck at least once by heavy ion particles. They estimated that roughly 20 million out of 43 million hippocampal cells would be hit by particles with atomic numbers greater than 15. The hippocampus is the brain region most critical for memory formation and spatial navigation, exactly the cognitive functions astronauts need most. Approximately 230,000 out of 1.8 million thalamus cell nuclei would be hit. The thalamus is a crucial relay station for sensory information and consciousness regulation. These are not estimates based on speculation. They are calculated from measured cosmic ray flux values and known cell geometries. The particles are there. The cells are there. The collisions will happen. And there is a related phenomenon that provides direct, visible evidence of cosmic ray particles passing through the brain. During the Apollo missions, astronauts reported seeing mysterious flashes of light. White streaks and spots would appear in their visual field approximately every 3 minutes during deep space transit. This occurred even with eyes closed and in complete darkness. The phenomenon was so consistent and so puzzling that NASA initiated a formal investigation called the Apollo Light Flash Investigation. The cause was eventually identified. Individual cosmic ray particles, particularly heavy nuclei, were passing through the astronauts' eyes. When these particles traversed the retina, they stimulated photoreceptor cells directly, either through ionization or through a phenomenon called Cherenkov radiation. Each flash that an astronaut saw was literally a single heavy cosmic ray particle passing through their eye at nearly the speed of light. A visible, direct demonstration that their bodies were being continuously bombarded. And if a particle can create a visible flash in the retina, imagine what similar particles are doing as they pass through brain tissue, through the cells responsible for thought, memory, and consciousness. Beyond the brain, cosmic radiation damages the cardiovascular system. A review published in Nature Reviews Cardiology by Hewson and colleagues in 2018 linked space radiation exposure to increased cardiovascular disease risk. Radiation causes inflammation in blood vessel walls, promotes atherosclerosis, and damages the cardiac muscle itself. For a Mars mission, researchers have estimated that the circulatory disease risk increases radiation attributable mortality by approximately 40%. Heart attacks, strokes, and other cardiovascular events become more likely not just during the mission, but for years and decades after return. There is also the eye itself. Apollo astronauts who flew lunar missions, which involved transit through deep space outside the magnetosphere, were found to have unusually high rates of cataracts later in life, compared to astronauts who only flew in low Earth orbit. Cataracts occur when the lens of the eye becomes clouded, gradually reducing vision. Cosmic ray damage to lens proteins causes them to aggregate and lose transparency. This is a cumulative, progressive effect that worsens with total radiation dose. For astronauts on missions lasting years rather than days, this could result in significant vision impairment during the mission itself. The immune system is another victim. Radiation suppresses immune function by damaging lymphocytes and other immune cells that circulate in the blood. These cells are among the most radiation sensitive in the body because they divide rapidly. An astronaut whose immune system is progressively weakened over months or years in deep space becomes vulnerable to infections that a healthy immune system would easily handle. On Earth, this would mean a trip to the doctor. In deep space, millions of kilometers from the nearest hospital, an infection that the body cannot fight could be fatal. One of the most illuminating studies on the comprehensive biological effects of space radiation is the NASA Twins study, published in the journal Science in 2019. This study took advantage of a unique opportunity. Astronaut Scott Kelly spent 340 days aboard the International Space Station, while his identical twin brother Mark Kelly remained on Earth. Because they share identical DNA, any differences observed between them could be attributed to the spaceflight environment rather than genetics. The results revealed numerous changes in Scott during and after his mission. His telomeres, the protective caps at the ends of chromosomes that typically shorten with age, paradoxically became longer during spaceflight. Then, upon return to Earth, they rapidly shortened, some becoming shorter than before the mission. Telomere instability is associated with accelerated aging and increased cancer risk. His gene expression patterns changed, with hundreds of genes showing altered activity. His immune function was modified. His cognitive performance, while not dramatically impaired at the IS radiation levels, showed some measurable changes. And remember, this was in low Earth orbit, where the magnetosphere still provides substantial protection. The radiation doses Scott received were a fraction of what a Mars crew would experience. If these changes occur at IS radiation levels, what would happen at 3 to 4 times that dose over 3 times as long a period? Now, if you are thinking that there must be a solution, that surely we can just build better shields, thicker walls, more protective spacecraft, then we need to talk about one of the most counterintuitive and frustrating problems in radiation physics. We need to talk about the shielding paradox. When you think of protection from radiation, the intuitive image is straightforward. You put material between yourself and the source. The denser and thicker the material, the better the protection. This works for many types of radiation. Alpha particles, which are helium nuclei emitted during radioactive decay, are stopped by a sheet of paper. Beta particles, energetic electrons, are stopped by a few millimeters of aluminum. Low-energy X-rays are significantly attenuated by lead. Even gamma rays can be substantially reduced by sufficient thickness of dense material. For solar particle events, which consist mostly of protons with energies below 1 billion electron volts, adequate shielding is achievable with reasonable amounts of material. Several centimeters of aluminum or, better yet, hydrogen-rich materials like polyethylene can significantly reduce speedoses. But galactic cosmic rays are a fundamentally different problem. The reason is their energy. GCR particles routinely carry energies of hundreds of millions to billions of electron volts per nucleon. An iron nucleus with an energy of 1 billion electron volts per nucleon carries an enormous amount of momentum. When it strikes a shielding material, it does not simply stop. It interacts with the atomic nuclei in the shielding, and several things can happen, none of them ideal. The GCR particle may undergo nuclear fragmentation, breaking apart into lighter nuclei and releasing individual protons and neutrons. The target nuclei in the shielding material may also fragment. These nuclear reactions produce a spray of secondary particles, lighter nuclei, free protons, free neutrons, pions, muons, gamma rays, and other radiation products. Many of these secondary particles are themselves highly energetic and highly penetrating. Here is the critical problem. Neutrons, which are electrically neutral, cannot be deflected by electric or magnetic fields and are extremely penetrating. They pass through material that would stop charged particles of the same energy. When heavy GCR particles fragment in shielding, they produce abundant secondary neutrons that can actually deliver more dose to the astronauts behind the shield than the original particle would have delivered without any shielding at all. This is the paradox. For certain thicknesses and types of material, adding shielding makes the radiation environment worse, not better. For the astronauts inside, the shield converts a few very high-energy particles into many lower-energy secondary particles that collectively deposit more total dose in human tissue. This effect is thickness-dependent. Very thin shielding primarily produces secondaries without significantly stopping the primary particles, potentially increasing dose. Medium shielding begins to attenuate some of the secondaries, but is still insufficient to stop the highest energy primaries. Only very thick shielding can provide significant net dose reduction, but the mass required is impractical for a spacecraft that must be launched from Earth. The International Space Station's aluminum walls provide approximately 20 grams per square centimeter of shielding. This is woefully inadequate for GCR protection and may in fact slightly increase the dose from the highest energy heavy ions due to secondary particle production. Studies have confirmed that behind 50 centimeters of aluminum shielding, the dose from certain components of the GCR spectrum can actually be higher than in unshielded free space. Part 2. To provide truly effective protection against galactic cosmic rays, you would need shielding equivalent to what Earth's atmosphere provides, approximately 1,000 grams per square centimeter. That is 10 meters of water. 3 meters of concrete. For a crewed spacecraft, this would mean surrounding the habitable volume with meters of material, adding hundreds or thousands of tons to the spacecraft's mass. With current launch costs of several $1,000s per kilogram to orbit and the engineering challenges of assembling such a massive structure in space, this approach is entirely impractical with existing technology. Material choice makes a significant difference. Aluminum, the traditional aerospace material, is actually one of the worst choices for GCR shielding because of its relatively high atomic number. When heavy GCR particles hit aluminum nuclei, they produce abundant secondary particles, including many neutrons. Hydrogen-rich materials like polyethylene are much better per unit mass because hydrogen nuclei are close in mass to the incoming protons and neutrons, making energy transfer more efficient during collisions. Water is also effective for the same reason. NASA uses polyethylene panels on the ISS as supplemental radiation shielding. ESA's Rossini studies identified lithium hydride as particularly promising due to its combination of low atomic number and structural properties. But even with optimal materials, the dose reduction achievable at practical thicknesses is limited to roughly 20 to 35% for GCR. You cannot eliminate the problem. You can only partially mitigate it. The physics of nuclear fragmentation and secondary particle production creates a floor below which passive shielding cannot reduce the dose without impractical mass. This is fundamentally different from every other engineering challenge in space. Vacuum, we can build pressure vessels. Extreme temperatures, we have insulation and thermal control. Microgravity effects on the body, we have exercise equipment and countermeasures. Even meteoroid impacts can be guarded against with Whipple shields. But for galactic cosmic radiation, the laws of nuclear physics itself conspire to make the problem intractable with passive shielding alone. You are fighting against particles so energetic that they fragment rather than stop, creating new dangers in the process of trying to block the old ones. It is as if the universe designed a weapon specifically to be unblockable, and in a sense, it did. The same processes that created the heavy elements in your body, supernova explosions and neutron star mergers, also created the cosmic rays that now threaten your survival in space. The universe gives and takes with the same hand. Let us pause here and consider what we have established so far. We have a radiation environment in deep space that delivers approximately 1.84 millisieverts per day to unshielded astronauts. We have established that this radiation causes cancer, brain damage, cardiovascular disease, cataracts, immune suppression, and genetic alterations. We have established that conventional shielding cannot adequately protect against it due to the secondary particle problem and the impractical mass requirements. Now let us put real numbers to the problem of a Mars mission, because this is the nearest term deep space exploration goal and the one for which we have the best data. The reference Mars mission that most space agencies plan around involves approximately 1,000 days total mission duration, roughly 180 days for the outbound transit from Earth to Mars, approximately 500 days on the Mars surface waiting for the planets to align for the return journey, and roughly 180 days for the return transit. During the two transit phases, astronauts are in interplanetary space with no planetary body nearby for shielding. During the surface stay, they have the benefit of Mars itself, blocking radiation from below, and a thin Martian atmosphere. The Mars atmosphere helps with solar particles and the lowest energy GCR, but is nearly transparent to the bulk of the GCR spectrum. The RAD instrument on Curiosity measured 1.84 millisieverts per day during transit and 0.64 millisieverts per day on the Mars surface. Using these values, we can calculate transit dose equals 360 days times 1.84 millisieverts per day equals approximately 662 millisieverts. Surface dose equals 500 days times 0.64 millisieverts per day equals approximately 320 millisieverts. Total mission dose equals approximately 980 millisieverts, essentially 1 sievert. 1 full sievert of radiation dose over 1,000 days. For reference, the average person on Earth's surface receives about 3.6 millisieverts per year from all radiation sources combined. A Mars astronaut receives in 3 years what an Earth dweller would receive in approximately 270 years. The concentration of that exposure in such a short period overwhelms the body's repair mechanisms, which evolved to handle Earth's gentle trickle of background radiation. Now consider the career dose limits. NASA's current limit of 600 millisieverts means that a single Mars mission at approximately 1,000 millisieverts would exceed the limit by 67%. This is not a marginal exceedance, it is a substantial one. Under current regulations, NASA cannot legally approve a mission that would expose astronauts to this level of radiation unless the limits are changed, or unless effective countermeasures can reduce the dose to within acceptable bounds. ESA's more generous limit of 1,000 millisieverts is approximately matched by the expected Mars mission dose, meaning a Mars astronaut would use their entire career allocation in one mission with essentially zero margin for any additional spaceflight. These are not theoretical concerns. They are regulatory realities that are actively shaping mission planning right now. There is a temporal factor that makes this even more challenging. The cosmic ray intensity varies with the 11-year solar cycle, and this creates a genuine dilemma for mission planners. During solar maximum, when the sun is most active, the enhanced solar wind and magnetic field push more galactic cosmic rays out of the inner solar system. GCR dose rates during solar maximum can be 40 to 50% lower than during solar minimum. This suggests that the safest time to fly to Mars is during solar maximum. ESA has explicitly stated that solar maximum is the safest time to travel to Mars. However, solar maximum also brings the highest risk of intense solar particle events, like the August 1972 storm. These events can deliver hundreds to thousands of millisieverts in hours. So mission planners face a choice. Fly during solar minimum, lower risk of acute SPI exposure, but higher continuous GCR dose. Fly during solar maximum, lower GCR dose, but higher risk of a potentially lethal SPI. The current strategy is to plan for solar maximum launch to minimize the larger cumulative GCR exposure. For missions beyond Mars, the numbers become even more daunting. A mission to Jupiter, at approximately 5 astronomical units from the Sun, would require transit times of 2 to 6 years, depending on the trajectory. At 1.84 millisieverts per day, a 3-year transit would deliver approximately 2,000 millisieverts, twice the full ESA career limit. And Jupiter's own radiation environment, dominated by its powerful magnetosphere trapping particles into belts millions of times more intense than Earth's Van Allen belts, creates an additional extreme hazard. A crewed mission to Saturn or beyond would involve transit times of 5 to 10 or more years, potentially delivering 5 to 7 sieverts or more. At these levels, the radiation exposure is not just career-limiting. It is life-threatening in the acute sense. 5 sieverts delivered over several years would dramatically increase cancer risk, cause measurable cognitive decline, damage the cardiovascular system, and likely cause debilitating health effects long before the mission was complete. And then there is the ultimate boundary, interstellar space. Beyond the heliopause, where Voyager now travels, the full intensity of galactic cosmic radiation is present without any solar modulation. Based on Voyager measurements, GCR intensity in interstellar space is roughly 3 to 4 times higher than within the inner solar system. If deep interplanetary space delivers 1.84 millisieverts per day, interstellar space may deliver 5 to 7 millisieverts per day or more. For a mission to the nearest star, Proxima Centauri, at 4.24 light-years distance, even an optimistically fast spacecraft traveling at 10% the speed of light would require 42 years of travel time. At 5 millisieverts per day, that is over 76 sieverts total. 76 sieverts. This is an absolutely fatal dose many times over. Even with substantial shielding reducing the dose by 90%, the remaining dose would still be approximately 7.6 sieverts. Still potentially fatal. Still far beyond any survivable limit for an unmodified human being. This is why cosmic radiation is not just a challenge for Mars missions. It is a fundamental, physics-based wall that limits how far biological humans can travel in the universe. Now, I want to make something clear. Science does not accept defeat easily. Researchers around the world are actively working on solutions to the cosmic radiation problem. Some are incremental improvements on existing approaches. Others are revolutionary concepts that, if they work, could change everything. Let us examine the most promising avenues of research and honestly assess their potential and their limitations. The most conceptually appealing solution is active magnetic shielding. The idea is simple in principle. If Earth's magnetic field protects us from cosmic radiation, why not create an artificial magnetic field around a spacecraft? Generate a powerful magnetic bubble, a miniature magnetosphere that deflects incoming charged particles away from the crew habitat. This concept has been studied since the 1960s, and recent advances in superconducting magnet technology have renewed interest. In 2023, Ferrone and colleagues published a review in Applied Sciences describing the current state of research. NASA has patented a concept called the Deployed Electromagnetic Radiation Deflector Shield. The European Space Agency has funded feasibility studies. The physics is sound. Charged particles follow curved paths in magnetic fields. If you create a sufficiently strong magnetic field around a spacecraft, you can deflect incoming protons and heavy ions away from the crew. The stronger the field, the more energetic the particles you can deflect. But the challenges are enormous. To deflect the bulk of GCR, you need magnetic field strengths of several Tesla over volumes of hundreds of cubic meters. Current superconducting magnets can achieve these field strengths in small volumes, but scaling them up to spacecraft-sized volumes while keeping mass reasonable, providing continuous cryogenic cooling, and dealing with the structural forces remains an unsolved engineering challenge. There is also a fundamental physics limitation. Magnetic shielding only works on charged particles. GCR is entirely charged, so in principle, all of it can be deflected. However, any secondary neutral particles produced by interactions with the spacecraft structure, particularly neutrons, cannot be deflected magnetically. And the strong magnetic fields themselves may have biological effects on the crew. While static magnetic fields at a few Tesla are considered safe for short-term medical imaging, continuous long-term exposure to strong magnetic fields is less well studied and may have subtle physiological effects. The 2023 paper by Fochtman and colleagues in NPJ Microgravity, which outlined priorities for radiation research in the context of sustainable human space exploration, noted that it remains unclear whether a realistic active solution could provide adequate protection against the high-energy GCR component. The highest energy particles, those ion nuclei at tens of billions of electron volts per nucleon, would require impossibly strong fields to deflect at practical distances. So even a working magnetic shield might only partially solve the problem, deflecting lower energy GCR while allowing the highest energy particles through. The second approach is optimized passive shielding, which we touched on earlier. While no practical amount of passive material can eliminate GCR exposure, optimizing the choice and arrangement of materials can minimize it within engineering constraints. The key principles are: use low atomic number, hydrogen-rich materials, design multi-layer shields that promote beneficial nuclear fragmentation, and use multifunctional design where water tanks, food storage, equipment, and other necessary payload components are positioned between the crew and the space environment, serving double duty as radiation shielding. On planetary surfaces, in situ resource utilization offers more promising options. On the Moon, regolith can be piled on top of habitats, or habitats can be constructed in lava tubes. Several meters of regolith would provide substantial radiation protection. On Mars, similar approaches could work, burying habitats under Martian soil, building into cliff faces, or using ice deposits as shielding. Mars has an additional advantage in that the planet itself blocks radiation from below, and the Martian atmosphere provides some overhead protection. But these solutions only help on the surface. During the transit between planets, which for Mars takes 6 to 9 months each way, the crew is exposed in deep space with only what they brought with them. A storm shelter, a heavily shielded room within the spacecraft where crew retreat during solar particle events, can provide protection against SPEs. But crew cannot spend the entire 6 to 9 month transit in a storm shelter. It would be too small, too confined, and GCR is continuous anyway, making a shelter ineffective unless you plan to live in it permanently during transit. and a shelter with enough shielding for GCR would be too massive to launch. The third approach attacks the problem from the opposite direction. Instead of stopping the radiation, reduce the time spent in it. Faster propulsion systems that can cut Mars transit times from 6 to 9 months down to 2 to 3 months would dramatically reduce cumulative radiation exposure. Nuclear thermal propulsion, where a nuclear reactor heats hydrogen propellant to high temperatures and expels it at high velocity, could roughly halve Mars transit times compared to chemical rockets. Nuclear electric propulsion, using a nuclear reactor to power ion engines, could also significantly reduce travel time. More speculative concepts like fusion drives, antimatter propulsion, or laser sail systems could potentially reduce transit to weeks or days, though these remain far from practical realization. Reducing transit time does not eliminate the radiation problem. Even a 2-month transit at 1.84 millisieverts per day delivers over 110 millisieverts each way, plus the surface dose. But it reduces total mission dose from approximately 1,000 millisieverts to perhaps 400 to 500 millisieverts, potentially bringing it within career dose limits. For Mars, faster propulsion may be the most practical near-term mitigation strategy. For destinations beyond Mars, or for interstellar travel, even dramatically faster propulsion does not solve the problem because the distances are so vast that travel times remain long regardless. The fourth approach is biological countermeasures, modifying the human body to be more resistant to radiation damage. This includes pharmaceutical interventions such as radioprotective drugs that enhance DNA repair, reduce oxidative stress, or protect sensitive tissues. Research has identified several promising candidates. Amifostine, a drug originally developed for cancer radiotherapy patients, can protect normal cells from radiation damage. Antioxidants like N-acetylcysteine and various polyphenols can reduce the oxidative stress caused by free radicals. Nicotinamide riboside and other NAD+ precursors have shown promise in enhancing DNA repair capacity. However, none of these have been validated for long-term use in the chronic, mixed-field radiation environment of deep space. Their effectiveness against high, Let-Zer particles specifically is poorly characterized. And some radioprotective drugs have significant side effects that may be unacceptable for continuous use over years. A more radical biological approach involves genetic modification. The DNA repair mechanisms in human cells are powerful, but not the best that nature has produced. Some organisms are extraordinarily radiation resistant. The bacterium Deinococcus radiodurans can survive radiation doses thousands of times higher than would kill a human, thanks to highly efficient DNA repair systems and redundant genome copies. Tardigrades, microscopic animals capable of surviving the vacuum of space, produce a protein called damage suppressor that physically protects DNA from radiation damage. In principle, genes from these organisms could be introduced into human cells to enhance radiation resistance. Gene editing technologies like CRISPR make this technically feasible. Researchers have already demonstrated that expressing tardigrade DSUP protein in human cells in laboratory cultures reduces DNA damage from radiation by approximately 40%. But translating this to actual human astronauts involves enormous challenges. Genetic modification of humans raises profound ethical questions. The long-term effects of expressing foreign proteins in human tissues are unknown. The modifications would need to affect all tissues in the body, particularly the bone marrow, the brain, and the gut lining. Germline modifications versus somatic modifications present different risk and ethical profiles. And even a 40% reduction in DNA damage, while significant, does not eliminate the radiation risk for interstellar travel where doses are tens of sieverts. This approach could make Mars missions safer, but would not break through the interstellar wall. A fifth approach, still in very early research stages, is synthetic torpor, a state of induced hibernation that would reduce astronauts' metabolic rate during transit. In 2022, researchers led by Puspita Sari published results in scientific reports showing that synthetic torpor protected rats from exposure to accelerated heavy ions. The proposed mechanism is that reduced metabolic rate means fewer free radicals are produced from radiation interactions with water, and cellular repair processes may be enhanced during the metabolic slowdown. If astronauts could be placed in a safe hibernation state for the duration of transit, they would not need to be awake, would not suffer from boredom and psychological stress, would consume fewer resources, and might experience less radiation damage. But inducing safe reversible torpor in humans is not yet possible. We are not naturally hibernating animals, and the physiological mechanisms required are not fully understood. This remains a distant prospect. A sixth approach is improved space weather forecasting and operational procedures. This targets solar particle events specifically. If we can better predict when solar storms will occur and how intense they will be, astronauts can retreat to storm shelters in time to avoid the worst of the exposure. Current forecasting can provide minutes to hours of warning for SPEs. With improved solar monitoring and modeling, this warning time could potentially be extended, and predictions could become more reliable. This approach is practical and is actively being developed, but it only addresses the acute SPE component of space radiation. It does nothing about the continuous GCR background that is responsible for the majority of cumulative dose on long-duration missions. Electrostatic shielding is another concept that has been explored. Instead of using magnetic fields to deflect charged particles, use strong electric fields. By charging the outer surface of a spacecraft to high positive potential, incoming positively charged GCR particles would be repelled. However, maintaining such high voltages in the vacuum of space is technically challenging. The risk of electrical discharge, the enormous power requirements, and the practical engineering difficulties of creating and maintaining multi-million volt potential differences on spacecraft surfaces make this approach extremely difficult. It has received less research attention than magnetic shielding and remains largely theoretical. If we honestly assess the state of all these approaches, the conclusion is sobering. No single existing technology can solve the GCR problem for long-duration deep space missions. The most likely path forward for Mars missions is a combination approach, polyethylene or water shielding to reduce dose by 20 to 30%, storm shelters for SPE protection, faster propulsion to reduce transit time, possible pharmaceutical countermeasures to enhance biological resistance, and acceptance of a somewhat elevated cancer and health risk. For Mars, this combined approach might make missions feasible within the next few decades, though with clear residual risk. But for missions beyond Mars, and certainly for interstellar travel, none of these approaches individually or in combination can reduce radiation exposure to acceptable levels. The distances are too great, the energies too high, the physics too fundamental. Active magnetic shielding, even if perfected, would only work on charged particles and would require impractical power levels for the highest energy GCR. Passive shielding requires impractical mass. Faster propulsion helps, but cannot reduce interstellar travel times below years or decades without revolutionary physics. Biological modifications help at the margins, but cannot make humans immune to radiation at dose levels tens of times above the lethal threshold. This is the wall, not a physical barrier you can see or touch, but a gradient of increasing radiation intensity and cumulative biological damage that effectively limits how far biological humans can travel from the protective environments they evolved in. The further you go from Earth, the more protection layers you lose, the higher the radiation, and the shorter the time your biology can survive. Earth's surface, essentially unlimited time. Low Earth orbit, months to a year before significant effects. Deep interplanetary space, a few years before exceeding career limits. Interstellar space, unsurvivable for unmodified biological humans at any practical transit duration. This observation leads to profound questions about the future of space exploration, and, ultimately, about the future of humanity itself. If cosmic radiation creates a functional barrier to biological space travel at interstellar scales, what does this mean for our species? Are we permanently confined to the solar system? Is the dream of spreading to other star systems, of becoming a multi-stellar civilization, impossible for beings made of carbon and water and DNA? One possibility is that the solution lies not in protecting biological humans, but in transcending biological limitations entirely. Perhaps interstellar space is not meant for bodies like ours. Perhaps it is the domain of machines. Robotic spacecraft like Voyager are completely unaffected by cosmic radiation at the biological level. Their electronics can be radiation-hardened, protected with relatively modest shielding, or designed with redundancy and error correction to function indefinitely in the radiation environment of interstellar space. AI-driven probes could explore other star systems without any concern for biological vulnerability. They do not need food, water, or air. They do not get cancer. Their brain can be replaced or repaired. They do not suffer from cognitive decline. If we extend this thinking further, perhaps the long-term destiny of intelligent exploration is post-biological. Perhaps sufficiently advanced civilizations transfer their consciousness, their intelligence, their identity from fragile biological substrates to more durable artificial ones. A digital consciousness running on radiation-hardened processors could travel between stars without concern for biological degradation. This is speculative, of course, and raises its own philosophical questions about identity, consciousness, and what it means to be human. But the physics of cosmic radiation provides a concrete, measurable reason why biological interstellar travel may be fundamentally impossible, and why the solution may require not better shielding, but a complete transformation of what we are. Another possibility is that we never intended to travel between stars in our current form. Evolution is a process of adaptation, and if humanity does expand into space, the pressures of the space environment may drive evolutionary or deliberate genetic changes that produce descendants adapted to high radiation environments. Over generations on Mars or in space stations, with or without deliberate genetic modification, humans could diverge from their Earth-adapted ancestors. Enhanced DNA repair, more efficient antioxidant systems, radiation-resistant stem cells. Perhaps even fundamentally different cellular architecture. Such beings might be our descendants, but they would not be us as we currently exist. The wall of cosmic radiation might not stop the human lineage permanently, but crossing it might require becoming something different from what we are today. There is also a fascinating connection to the Fermi paradox, the question of why. If the universe is so vast and so old, we have not detected evidence of other intelligent civilizations. Many explanations have been proposed. Perhaps intelligent life is extremely rare. Perhaps civilizations tend to destroy themselves. Perhaps they exist but are not communicating in ways we can detect. But cosmic radiation suggests another possible factor. Perhaps every biological civilization, no matter how technologically advanced, faces this same invisible wall. Perhaps the radiation environment of interstellar space is a universal barrier that confines biological beings to their home star systems. If interstellar travel is effectively impossible for biological life, then the galaxy could be teeming with civilizations that are each confined to their own stellar neighborhoods, unable to bridge the vast irradiated voids between stars. Not for lack of intelligence or desire, but because the fundamental physics of the universe places a biological speed limit, a survival limit, on how far flesh and blood can go. This is a humbling thought. We often imagine that technology can overcome any obstacle given enough time and ingenuity. And perhaps it can. Perhaps solutions exist that we have not imagined, physics we have not discovered, materials we have not conceived of. But as of our current understanding of physics, the cosmic radiation barrier appears to be real, fundamental, and enormously difficult to overcome for biological organisms. It is written into the fabric of the cosmos itself, a consequence of the same violent astrophysical processes that created the heavy elements our bodies are made of. The same supernovae that forged the iron in your blood also launched the iron nuclei that would destroy your brain cells if you ventured too far from home. Let me bring this all together now with a comprehensive picture of what we have learned. We started with a terrifying near miss in 1972, when a solar storm of unprecedented power erupted between two Apollo missions and could have killed astronauts had the timing been slightly different. This introduced us to the reality of acute radiation danger in space. We then examined the nature of cosmic radiation itself, learning about galactic cosmic rays, particles from outside our solar system, accelerated by supernovae and other catastrophic events, to energies up to and beyond 320 exa-electron volts. We learned about Zer particles, the heavy nuclei that create devastating tracks of destruction through biological tissue, causing clustered DNA damage that overwhelms cellular repair mechanisms. We explored Earth's four-layer protection system, the heliosphere, the magnetosphere, the atmosphere, and the surface environment that allows us to experience only a fraction of a millisievert per year from cosmic sources. We saw how each layer lost during space travel exponentially increases radiation exposure, from 0.3 millisieverts per year at sea level to 180 to 360 millisieverts per year in low Earth orbit, to approximately 670 millisieverts per year in deep interplanetary space, to potentially over 2,000 millisieverts per year in interstellar space. We examined the biological destruction caused by this radiation, nerve damage leading to cancer, brain cell destruction leading to cognitive decline, cardiovascular damage, cataracts, immune suppression, and telomere instability. We saw real data from the NASA twin study, from animal experiments at Stanford Medicine, from calculations by Curtis and colleagues on brain cell hits during a Mars mission, and from epidemiological studies of astronaut health. We confronted the shielding paradox, the counterintuitive fact that conventional shielding can make the radiation problem worse due to secondary particle production, and that practical shielding cannot significantly reduce GCR without impractical mass. We calculated the specific doses for a Mars mission and showed that this exceeds career limits at major space agencies. We projected how these numbers grow dramatically worse for missions to the outer planets and to interstellar destinations, where doses of tens of sieverts make biological survival impossible with any foreseeable technology. And we surveyed the solutions being pursued: active magnetic shielding, optimized passive shielding, faster propulsion, biological countermeasures, synthetic torpor, and space weather forecasting. None individually or in combination can currently solve the problem for interstellar travel, and even for Mars missions, they can only reduce the substantial health risks. The picture that emerges is one of a graduated barrier, an invisible wall that becomes progressively more impenetrable the further you travel from Earth. It is not a wall in the sense of a physical obstacle you bump into, It is a wall in the sense of a limit beyond which survival becomes progressively less possible. Like the temperature gradient in a furnace, you can withstand the warmth at the edges, but the deeper you go, the more certain your destruction becomes. Cosmic radiation creates a thermal envelope around our planet, a zone of relative safety that extends to low Earth orbit for reasonable durations, reaches its practical limits somewhere around Mars for missions of a few years, and becomes absolutely lethal in the interstellar medium for any journey lasting more than a few years without revolutionary countermeasures that do not yet exist. This is perhaps the most profound invisible boundary in the universe for biological beings like us. We can see the stars. We can study them. We can send our machines to photograph them from afar. We can detect their planets and analyze their atmospheres. But reaching them with our fragile bodies of carbon and water, reaching them and arriving alive and functional and capable of actually experiencing them, may be the one thing we cannot do. Not because we lack courage, not because we lack intelligence, not because we lack ambition or resources, but because the universe itself, through the relentless bombardment of high-energy particles from ancient supernovae, has placed a biological limit on how far flesh and bone can travel. And yet, the story does not end in despair. The history of science is filled with barriers that were once considered absolute and later proved surmountable. The sound barrier was once thought to be an impenetrable wall for aircraft. The heat barrier of atmospheric re-entry was once considered unsolvable. Even space travel itself was once dismissed as impossible science fiction. Perhaps the cosmic radiation barrier, too, will eventually yield to human ingenuity in ways we cannot currently imagine. Perhaps there is physics we have not yet discovered, materials we have not yet synthesized, biological modifications we have not yet conceived, or entirely different approaches to the problem that will emerge from future research. What we can say with certainty is this: as of our current understanding of physics and biology, cosmic radiation represents the single most formidable, invisible barrier to human expansion into the cosmos. It is not a problem that money alone can solve. It is not a problem that political will alone can overcome. It is a fundamental interaction between the physics of high-energy particles and the chemistry of biological molecules. And solving it requires either overcoming that physics or changing that chemistry. Either we must find a way to stop the unstoppable, or we must find a way to survive the unsurvivable. Either option requires breakthroughs that have not yet occurred. The universe created us on this planet, wrapped us in layers of protection so perfect that we barely knew the danger existed, gave us minds curious enough to look up at the stars and dream of reaching them, and then placed an invisible wall of atomic shrapnel between us and our dreams. Not out of malice, not as a test, simply because that is how the universe works. Supernovae forge elements and scatter cosmic rays in the same event. The processes that gave us the carbon in our cells gave us the particles that would destroy those cells if we ventured beyond our protective cocoon. We are made of stardust, and we are threatened by star-born violence. Both facts are consequences of the same cosmic physics. Whether we eventually overcome this barrier or not, understanding it changes how we see ourselves in the universe. We are not invincible explorers for whom space is simply a matter of engineering. We are fragile biological organisms that evolved in a very specific radiation environment, and that environment extends only so far. Beyond it lies a cosmos that is indifferent to our survival, filled with energies that would destroy us without notice or ceremony. Knowing this does not diminish the dream of space exploration. If anything, it makes every step we do take into space more remarkable. Every astronaut who has floated in low Earth orbit, every human who has walked on the moon, has done so while being continuously bombarded by cosmic radiation, accepting a risk that most people cannot even comprehend. Their courage is all the greater for the invisible danger they face. And the quest to solve this problem, to find a way through the invisible wall, is one of the most important scientific endeavors of our time. Because if we succeed, the stars are open to us. And if we fail, then perhaps our destiny is not among the stars as biological beings, but as something else. Something we have yet to become. Either way, the cosmic radiation barrier forces us to confront fundamental questions about who we are, what we are willing to sacrifice, and what we are willing to become in pursuit of the infinite frontier. The next time you look up at the night sky, at those peaceful points of light scattered across the darkness, remember what fills the space between them. Not emptiness, not silence, but a ceaseless storm of particles, ancient and energetic and invisible and deadly, flowing through every cubic centimeter of that darkness at the speed of light. A wall you cannot see. A wall you cannot feel. A wall that the universe built not to stop us specifically, but that stops us nonetheless by the simple physics of what we are made of and what cosmic rays can do to those materials. An invisible wall that we cannot pass. Not yet, perhaps not ever with our current form. But understanding it, mapping it, measuring it, acknowledging its reality, this is the first step. Because you cannot overcome a barrier you refuse to see. And now, you see it. The question is, what do we do about it? The answer may define the entire future of our species. Whether we remain a single-planet civilization or become something that crosses the great irradiated void between the stars depends on our ability to solve this one invisible problem. The engineers are working. The biologists are researching. The physicists are calculating. The clock is ticking. And the cosmic rays continue to flow, as they have for billions of years, indifferent to our ambitions, indifferent to our dreams, obeying only the laws of physics that govern everything in this vast, beautiful, and profoundly dangerous universe. Now let me take you deeper into something that most discussions of this topic overlook. The radiation environment in space is not uniform. It is not static. It varies in ways that add additional complexity to an already difficult problem. Understanding these variations is crucial for anyone attempting to plan a real mission beyond Earth orbit. The galactic cosmic ray flux within our solar system is modulated by the solar cycle. The Sun's activity follows an approximately 11-year cycle, alternating between periods of high activity and low activity. During solar maximum, the Sun produces more solar wind, more coronal mass ejections, and a stronger interplanetary magnetic field. This enhanced magnetic environment acts like a more powerful shield against incoming galactic cosmic rays, reducing GCR flux in the inner solar system. During solar minimum, solar activity drops, the solar wind weakens, the interplanetary magnetic field becomes less turbulent, and more GCR penetrates inward. The variation is significant. GCR dose rates during solar minimum can be 40 to 50% higher than during solar maximum. This means the timing of a mission matters enormously. Launch during solar minimum, and you face the highest chronic radiation background. Launch during solar maximum and the chronic background is lower. But you face the highest probability of being hit by a major solar particle event. This creates a genuine strategic dilemma with no perfect solution. The current consensus among space radiation experts, as articulated by ESA, is that solar maximum is actually the preferable launch window, despite the SPI risk. The reasoning is that SPI risk can be mitigated operationally through storm shelters and contingency procedures, while GCR exposure cannot be mitigated by any operational measure during transit. You can hide from a solar storm for a few hours to days, You cannot hide from GCR for 6 months. Therefore, it is better to accept the manageable acute risk in exchange for a lower chronic background. But this strategy requires reliable space weather forecasting and sufficiently capable storm shelters, neither of which is currently adequate for a deep space mission. The spatial distribution of cosmic radiation also varies in ways that matter. Within Earth's magnetosphere, there are regions of higher and lower radiation intensity, depending on orbital inclination and altitude. The South Atlantic anomaly, a region where the inner Van Allen belt dips closest to Earth's surface due to an asymmetry in Earth's magnetic field, exposes spacecraft in low Earth orbit to elevated radiation during passes through this area. IS astronauts receive a disproportionate fraction of their total dose from passes through the SAR. Beyond Earth's magnetosphere, the radiation field is more uniform, but not perfectly isotropic. There are slight directional preferences in the GCR flux, depending on the structure of the local interstellar magnetic field and the geometry of the heliosphere. But for practical purposes, once you are in deep interplanetary space, the radiation comes from all directions approximately equally. There is no safe direction to point your spacecraft. You are immersed in a bath of radiation with no preferred orientation. Temperature variations in the cosmic ray energy spectrum also have implications for shielding design. The spectrum peaks at energies of a few 100 million electron volts per nucleon, meaning most particles have energies in this range. At these energies, optimized passive shielding can provide meaningful dose reduction. But the spectrum extends to much higher energies with a power law tail, and particles above several billion electron volts per nucleon cannot be significantly attenuated by any practical passive shielding. These ultra-high energy particles are rare individually but contribute meaningfully to the total biological dose because of their high LET values and the quality factors applied to high LET radiation. The most damaging particles are simultaneously the hardest to stop. This is yet another way in which the cosmic radiation environment seems almost specifically designed to be intractable. Let me now address a question that thoughtful viewers may be asking. If cosmic radiation is so dangerous, how do astronauts currently survive on the ISS for months to a year? Why are they not immediately debilitated by the effects I have described? The answer lies in the distinction between the ISS radiation environment and deep space, the distinction between acute effects and long-term effects, and the remarkable but limited capacity of the human body to repair radiation damage. The ISS is in low Earth orbit, still within the protective embrace of Earth's magnetosphere. ISS astronauts receive approximately half to 1 millisievert per day, compared to 1.84 millisieverts per day in deep space. Additionally, Earth itself physically blocks radiation from below, further reducing exposure. The total dose for a 6-month ISS mission is approximately 80 to 160 millisieverts. At these levels, the body's DNA repair mechanisms can largely keep up with the damage being inflicted. Single-strand DNA breaks are repaired within minutes to hours. Most double-strand breaks are repaired within hours to days, though with a small probability of error. The rate of unrepaired or misrepaired damage is low enough that the body can function normally during the mission. The effects are long-term and statistical: a slightly elevated lifetime cancer risk, possible earlier onset of cataracts, potential cardiovascular effects that manifest years to decades later. But during the mission itself, ISS astronauts function normally. In deep space, the situation is quantitatively different. The dose rate is 2 to 4 times higher, meaning the rate of NAR damage is 2 to 4 times higher. A Mars mission lasts approximately 3 times longer than a typical ISS stay. And critically, the proportion of high LETSA particles is higher in deep space. In deep space, without the magnetosphere, you get the full spectrum, including abundant lower energy particles that are still above the shielding threshold. The combination of higher dose rate, longer duration, and different radiation quality means that repair mechanisms may begin to be overwhelmed. The accumulation of unrepaired damage grows faster than on the ISS. Cognitive effects may manifest during the mission. Immune suppression may become clinically significant. The difference between an ISS mission and a Mars mission is not merely quantitative. It may cross a qualitative threshold where repair mechanisms can no longer maintain tissue function at normal levels.